Hello! In this video we'll be discussing the mesh current analysis technique, which is the companion tool to the node voltage analysis, where the node voltage used Kirchhoff's current law as the base principle. Mesh current analysis actually uses Kirchhoff's voltage law. And you'll see why here in a minute. So I've got this circuit laid out here. This is the exact same circuit that's in your notes. So if you don't have them out already, I encourage you to at least bring them up in another window. Just pause the video and take a look at those. Mostly because the handwriting on here is a little hard to read when it gets a bit small, so all these independent voltages might get mixed up on the video. So looking at this, we've got the same circuit that we were using for our node voltage. We have a 12-volt source, and we've got 5 resistors. We don't know what any of the voltages or any of the currents are here except for what's on the independent, but we can find out. To start using the mesh current analysis, what you want to do is define closed paths, like we do with using the voltage law. And we call these current loops, or mesh current loops. So my first one I'm going to define as going in a clockwise direction. In this, we call them windows. So you can kind of see there's this blank spot in between all these components. That'd be a window. We'll call that I1. So for window 1, we have our first mesh current. Next, I'll do the second window here. We'll do I2. And then, of course, the third window will be up here. Now, you don't have to define them all in the same direction, but it will make it easier for you in the long run, simply because of how signs get all tangled up. Now, a mesh current is a little harder, especially for me, maybe not for you, to understand compared to the node voltage. They're kind of imaginary currents. We're saying that this current I3, for instance, that's the current that's flowing through that loop. There's no other currents through there. Of course, we know that's not true just looking at this, because we've got I2. So across, say, that 6 ohm resistor, we have a competition between I2 and I3. Well, we can solve those out, and I'll show you how. So using our voltage law, we'll take V1, V2, and V3. Those are the 3 voltages in current mesh current I1. So V1 is the voltage across the source, V2 is across the 8 ohm, and V3 is across the 2 ohm. And let's put those up here. V2 plus V3 plus V1 is, of course, equal to 0. Now, like we did with node voltage analysis, we're going to substitute in currents and resistances for those voltages. So V1, well, that's easy. That's just 12. But if you remember from the direction of our I1, we're coming through the negative terminal. So we're going to subtract that. We defined V2 as going from positive to negative. So we add V2, and we can replace it with this. We take the resistance, so 8, and multiply by the difference between I1 and I3. And we do the same for V3. So in this case, we have a 2 ohm resistor, which we're adding since we're going through the positive to the negative. So we add 2 times I1 minus I2. And this equals 0. Okay, so that's our first equation. We have 3 mesh currents. We're going to have 3 equations for our system. So next, let's do I2. So we start with V4, which is a differently defined voltage than V3. Note that V4 is an opposite polarity to V3. So if I have negative V4, what I actually have is V3. So to calculate that, all I would need to do then is change the order on my currents. So all I would do, 2 I2 minus I1. And we can see that that term is just flipped around compared to what we had for V3 in our previous equation. This looks a little screwy, but trust me, it'll all work out in the end. So we have V4 there. We need V5, which is across the 6 ohm resistor. We go from positive to negative there. So we have 6 I2 minus I3. And last, across the 4 ohm resistor, we just have V6, 4 times I2 equals 0. Our third equation then is going to be for I3. We'll start with the 8 ohm resistor. So V7 plus V8 plus V9. So we've got 8 times I3 minus I1 plus I3 times 10 plus V9, which is 6 I3 minus I2 equals 0. Okay, so we've got all these equations. We could solve them. It'd take a little while. We stick them in a calculator or into MATLAB. If you look, I encourage you to do this yourself in MATLAB, but if you look in the notes, we have a set of currents, I1, I2, and I3, that don't actually correspond to anything, right? Those are just the mesh currents. So I1 isn't any current in a particular branch. It's simply a value of that mesh current. But what we can do is now sub those back in to these systems of equations and get out our voltages. So on the node voltage, our V3 was equal to roughly 2.56 volts. Let's check that on here, see if we get the same answer. So our V3 was here, and its opposite was here. So it should then also equal 2 times I2 minus I1, which is just, if we look in our notes, 2 times the difference between 0.786 minus 2.06. Remember, this is amps, because we're getting a voltage. 2 ohms times this different in amps. And the answer I get on my own calculator is negative 2.548. I'm sorry, I was calculating V4. So this is V4. So we have a negative here. V3 then is just going to be the opposite, right? So we take the same, so flip them, so I1 minus I2, 2.06 minus 0.786. And V3 is just equal to the reciprocal. Sorry, not the reciprocal, but the opposite sign. And that holds up, right? V4 equals negative V3 and vice versa. So what we've done here is we've replaced these voltages with a difference in currents. This one's a little more abstract, I think, than the node voltage, but it's just as valuable of a tool. Let's try another example. Now in this case, we're going to have a voltage source, like we did with our node voltage, where we had to use a supernode. So in this case, we have 8 ohm resistor here. We'll replace the 10 ohm resistor with a voltage source. Well, that's really nasty. voltage source plus minus 4 ohm resistor here. Have one more voltage source here. Our 2 ohm resistor in the middle. Now, let's just use their nominal values. So we've got our 12 here. This will just be a 10 volt source. And here we'll just have our 6 volt source. In mesh current, this is really easy. Just like current sources were really easy in node voltage. So in this case, all we do is we replace those voltages, or the resistance in the current with these voltages, like so. So our first window, we have again here, I1, here, I2, and here, I3. So let's do I1. Well, we go up through the 12 volt source, through that negative terminal, so we subtract it. Come across that 8 ohm resistor, so 8 times I1 minus I3. And last, we come down the 2 ohm source. So 2, oh man, this pen is all over the place. Plus 2 times I1 minus I2. You'll note there's a little pattern here. Whatever system we're solving, we always put the mesh current that we're describing first. So it's always I1 minus I3 or I1 minus I2, and vice versa when we move to the next set. For example, here. So I2 then, looking at this, will come up through the 2 ohm resistor. So 2 I2 minus I1. Then we come to this voltage source. Well, that's easy, right? In this analysis, all we have to do, look at the polarity on that voltage source and subtract it. Then finally, we have the last in our 4 ohm resistor. And similarly, for mesh current 3, we'll start at the 8 again. So we go 8 minus I3 minus I1 up to that 10 volt source, which again, we just have to subtract since we're coming through the negative terminal. Plus, well, we come through the positive terminal at 6 volts this time, so plus 6. And that equals 0. This is a lot easier to solve, isn't it? We've got quite a fewer of these I minus I terms. So voltage sources are easy. Problem comes when we get to current sources. And in that case, we have to use a super mesh. Alright, so let's try that example. Now, we'll add a bit of complexity here. Little 12 volt source as normal. We'll come up with our 2 ohm resistor. Come down with a 10 ohm resistor. So this will be our first loop. We'll call that I2. Come up. Oh, let me match the notes on this. We'll take this as I1. Oh, sorry, I2. What was I2? Oh boy. Oh, okay. Rewrite that real quick. Sorry about that. So we have I2. We have a 4 ohm resistor up here. This branch comes down. We have an 8 ohm resistor here. We get to the tricky part. Put in a current source. We'll define this as I1. We'll put resistor here in parallel. This will be our I3. And finally, one more resistor here. So 14 and 12. And define our last loop, I4. Okay. So you can kind of figure with supermesh that we're going to have to combine some stuff. But let's see where we get to. Oh, hello. Let me pause this 1 second and get rid of this thing. Okay, back in ship shape. So first we go through our normal equations. We have our I2 minus I3s. So let's start that out. So negative 12 plus I2 times 2. And then we have our last term, which is across that 10 ohm resistor. So plus 10 times I2 minus I3. Right up at the top really isn't working out for me. Plus 10 I2 minus I3. Okay, so that's our first mesh. I3 then, well, that's going to be complicated. Okay, so let's skip that one. We'll go to I4. Alright, so first we've got a 12 ohm resistor. So 12 times I4 minus I3. Now we have, oops, did not label that. That's our 8 ohm resistor. We have the 8 ohm resistor here, plus 8 I4 minus I1 plus 14 I4. Okay, so those are the two easy ones. But now we've got that current source in there. And that's going to give us a headache. Alright, so looking at this, I'm going to need to define our current source. We'll say 6 ohms. Okay, that gives me one more piece of information, because I know that the current on there is 6. So I can just write it like this. 6 is equal to I1 minus I3. I1 minus I3. Now why did I do it I1 minus I3 and not I3 minus I1? Well, if we look at how our meshes are set up, I1 is going clockwise just like I3. But along that branch, I1 is facing in the same direction as that current source, whereas I3 is facing in the opposite direction. And we know when you have it going in the same direction, we're going to add it, and when we need to go in the opposite direction, just flip the sign. So in this case, I3 is negative, whereas I1 is positive. Now, I still need one more equation, because I've got 4 unknowns. What I can do is define a new mesh that doesn't touch that current source. So what we're going to have to do is go right around the outside there. So we define a new mesh right along this periphery here. So from the 10 ohm up to the 4 ohm, down to the 14, and then back to the 10. There's another path you could take if you wanted to. It doesn't matter. The important thing is we have to get that 4 ohm resistor in there. So the other path you could take goes along here and cuts out that corner instead. Either of those is fine. They're both valid because they both had that 4 ohm resistor. We need that 4 ohm resistor because it's a puzzle piece of our equations. Without it, we wouldn't have linearly independent equations and thus would not be able to solve them. So we wouldn't have enough information. Okay, so let's do this one. This is a big one. Alright, so we've got first we'll take the 10 ohm. So we go 10 I3 minus I2, which is just the voltage on that 10 ohm resistor. We go up to the 4, and all we have touching it is I1. Then go over to the 14. And there we also only have one current touching it, I4. And that, of course, has to equal 0. So now we have 4 pieces of information. Now we have 4 pieces of information. And from this we can solve it. So given a current source, we're able to identify one piece of information by looking at the meshes and which ones align with that current source. And I'm putting an equation together for it. And then we're able to create a supermesh, which is just a new mesh out of a different closed path. Now remember, this is voltage law, so all these are closed paths. And as long as you have the closed path, you'll be alright. So if this were a problem you needed to solve, we can stick it into MATLAB, get each of the variables, and then we would have each of those voltages that we've been writing down. That's all for today. Thank you.